Hello, everyone. Good morning, good afternoon, good evening, wherever you are in the world. Welcome to this Asynt webinar. We have run a series of these webinars this year. You can find those all online. But today we're going to be introducing the concepts of how to use pressure reactors and run pressurized reactions at high temperatures and pressures. So we're going to give a brief introduction to some examples, some of the pitfalls that we can find. Today we have a special guest speaker, Steve Howdle from the University of Nottingham, who has worked with Asynt in the past to help develop a specific pressure reactor, and Steve will be talking about that later. So if you bear with me, I'm just going to put up a slide deck. Yeah, so as I said, welcome everyone to this introduction to working safely with high pressures webinar. So we are going to be running through a few topics, as I said. There's the agenda here, but I won't dwell on this as we'll be covering all of the topics anyway. So just to begin with, I wanted to introduce our guest speaker, Professor Stephen Howdle. Stephen has been leading a group at the University of Nottingham for many years, working with polymers and supercritical fluids. So his main interests are in supercritical carbon dioxide work, using that as a new solvent for polymer synthesis. And Stephen will be demonstrating a case study of this, demonstrating a video of that later. My name's Andrew Mansfield. I'm the technology manager here at Asynt. If you have any questions about pressure reactions or any of our range of products, you can contact us at enquiries@asynt.com. So I just wanted to start off by just introducing a few types of reactions that we'd be looking at high temperatures and pressures. Now, the first one here I have here is hydrothermal synthesis, and this is really a method of synthesizing materials, particularly inorganic materials, at high temperatures and pressures using aqueous solutions, and that enables us to perform the growth of crystals with unique properties. So if you look at the slides here, the reaction conditions that we're using are elevated, so they're above our aqueous boiling point, and we're using these at reasonable pressures as well. And we're doing this because water at high temperatures and pressures allows us some specific properties. But there are associated hazards with doing this, obviously the high temperatures and pressures. So we do have explosive hazards if our reactor, our autoclave, is overfilled or heated too quickly for these types of reactions. So we only use rated autoclaves, and there is a consistent theme through lots of these reactions is that we need reactors that we are confident that have the certification and the pressure and temperature ratings that we want to carry out our reactions under. So we should only use rated autoclaves with these types of reactions. And we also need to consider the safety aspects. So we're working, as I said, at elevated temperatures and pressures. So we need proper shielding. We need relief valves for overpressurization, and avoid methods or avoid catastrophes where we may leak within our reactor. The next example is similarly themed. Excuse me. So these are solvothermal type organic reactions. So in these reactions, we are analogous to kind of microwave heating. We are taking our organic solvents way above their boiling points. We're using pressure to keep those in liquid form. So we are typically using, again, high temperatures, and we are inducing high pressures. We can use these types of reactions for, formation of heterocycles, carbon-carbon, carbon-nitrogen type bonds, and MOF synthesis. But again, we need to consider the reaction vessel that we're using. The glass is okay up to a certain pressure, but it's not okay at high pressures. So then we need to look at properly pressure-rated autoclave reactors, typically stainless steel. And again, we need shielding. That's mandatory. The next example here is hydrogenations. So hydrogenations are pretty familiar to most chemists. It's a reaction for reduction of unsaturated bonds in organic compounds, and we typically use a precious metal catalysis and molecular hydrogen. Again, we're working at higher pressures. Sometimes we'll use much higher elevated temperatures, because a lot of these reactions can be quite sluggish. Some of them are quite quick, but we need a high hydrogen concentration. Now, using hydrogen has a specific safety aspect in its own right. It's extremely flammable. And often the catalysts we use are also pyrophoric. So we need to incorporate that risk assessment as well as managing the reaction vessel that we're going to carry out our reaction in. Again, all of these vessels need to be purged carefully. We need to think about how we expel our reactive gas as well. Now, the last example here is one that we're going to touch on later, and that's using supercritical fluids. Now, supercritical fluids are substances at a temperature and pressure above its critical point, have a distinct phase between liquids and gas. These can impart lots of properties. As Steve is going to be speaking about later, it's a very green solvent. We can use this for things like polymerizations and extractions. But again, to get to that supercritical point, we need elevated pressures and often temperatures. When we're working with pressurized gases, we need to think about the hazard of maybe a catastrophic vessel failure. That would mean the evacuation of high pressure gases. So we need to think about the expulsion with some kind of breach in our reactor, but also that rapid decompression, especially if we're using things like carbon dioxide, can give frostbite. We need to be careful about that freezing property. So we need to use specified equipment, as we've discussed, and we also need to think about those safety relief valves to depressurize for unwanted events. So that's a few examples of reactions where we might want to use elevated temperatures and pressures. They all have associated hazards, and they're all quite common. So if we just recap on some of those, what are those hazards? So the general hazard for these types of reactions is overpressurization. That's the single largest risk. So we need to think about properly rated pressure vessels that we know can operate under the conditions we want to operate at, but also have the analogous rated pressure relief system, whether that's a burst valve or a pressure release valve. We need to think about explosion risks. If we're using combustible gases like hydrogen, as we spoke about previously for hydrogenations, these can ignite easily. So we need to think about the safety implications of using these gases and for all of our local safety rules and risk assessments. Lots of these reactions are exothermic, so we need to think about proper temperature and heat management, whether that's heating our reactor, but also cooling. And we can do that with jacketed, with autoclave reactors, with pressure reactors. Again, if we're using things like supercritical CO2, we need to think about cryogenic burns and the toxicity of the material that we're using. And this is part and parcel. This is all rolled into our local risk assessment that we use for assessing our reactions before we carry them out. But an underlying factor here is making sure that our equipment is integral to the reaction we want to carry out. Does it have the right pressure rating? Is it made of the right material? And at high temperatures and pressures, we need to inspect our equipment before we perform any reaction. So there's a few of the associated risks of doing these types of reactions, pressurized reactions outlined here. But a while back, we wrote a small blog piece for just some simple steps that we can use to carry out, or we can carry out to help us run pressurized reactions safely. Now, these are all on the Asynt website, but I'll post a link when we send out the recording of this webinar. And they're pretty self-explanatory. But if you follow a lot of these, then, or if you follow all of these, then your experience of running pressurized reactions should run smoothly. The first one is maintenance. It doesn't matter whose reactor it is, if you've borrowed it from another lab or it's your own, the responsibility of looking after that and making sure it's fit for purpose should ultimately come down to you. So always inspect your reactor. We need to think about our reaction to begin with. That's probably primary to looking at the reactor itself. We need to identify all of the associated risks, those byproducts, and the circumstances where we may have loss of control of our reaction. So that's anticipating, planning, reducing, and avoiding all of those associated risks. And you do that by a thorough assessment of the reaction that you carry out. I shouldn't need to tell you that anyway. That's a risk assessment that all chemists should perform before they actually step into the lab. I've stepped forward a few paces. Part and parcel of all of this is following your in-house guidance. So we need to have awareness of our local lab safety rules. That's secondary to our risk assessment. Know where the fire precautions are, work in a well-ventilated area, and have all of those secondary safety procedures in place with your risk assessment. Then it's rec and construction limitations. As I've said through this already, we need to work with pressurized reactors that are suitable for the chemistry we want to carry out. Does it have the right material? Does it have the right safety aspects as far as pressure release valves in place? I've said links in structure, so it's not just the reactor construction, but it's things like links to temperature sensors or gas valves or even O-rings. All of these things need to be inspected before we carry out. We shouldn't underestimate all of that. Regarding vessel capacity, never overfill your autoclave. That massively reduces the risk. The more material you have, the more pressure you're going to associate with your reaction. Think about the temperature and pressure ratings. We've already covered that. So make sure that your reactor is fit for purpose. I skipped forward a slide earlier. Before we scale up any reaction, make sure that you run a small volume reaction first, and only increase this if you've really established a safe way to perform that. If need be, then running parallel reactions to get to your scales may be the safest way to scale up your reaction. As I said, think about all of the external safety. Think about your colleagues as well. Have you thought about your location? Are you doing this in a well-ventilated area? Do you have a safety screen for using combustible gases? Are these vented properly? And before you start, the reality check, the assessment of a colleague is always useful. Double check with the chemist next to you or your supervisor or whoever, and make sure that you understand all of the safety implications of the pressurized reaction that you're going to carry out. So that's all I was going to say in means of an introduction. I wanted to hand over to Professor Stephen Howdle. We've worked with Stephen over many years, and Asynt in the University of Nottingham, with Steve's guidance to create a range of pressurized reactors, specifically the PressureSyn that was developed at Nottingham that we now sell through Asynt, and it's available to you. But Steve's just going to give us a few thoughts, insights on how they went about overcoming some of those universal issues we've spoken about using pressure reactions, and some of the key considerations in the design of pressure syn. So that's enough from me. Over to you, Steve.
Okay, thanks, Andrew. So thank you everybody for coming along today. So I'm not going to give you a chapter and verse description of everything that we did. I'll just highlight a few points of why we went into high pressure and how we constructed the vessel. Andrew's going to show a video very soon, which will give you the idea of what we've done and how we did it. And how it works. So that will help you to visualize the things that I say. But I mean, the main thing to point out is that we're a university research group. So we wanted something that was quick, simple, and easy to use. And that's really been the fundamental thing that we had to get right. So when we were initially starting to move into high pressures, a lot of the kit that I could buy commercially was really quite complicated. And you had a lot of nuts and bolts and fittings that you had to screw up tight and to get it perfectly sealed. And it never really worked. So all of the kit that was out there was very difficult to work with. So working with our workshop at Nottingham, we thought about how we'd like to do it differently. And we wanted a very simple device that we could easily put together that wouldn't leak, that would be very safe to use, and then most importantly, when we took it apart, would be very easy to clean. So we didn't want nooks and crannies where things got stuck and meant that your next reaction or your next process might be contaminated. So when you see the video, when Andrew shows you that later, I hope you'll see some of those features coming out in how we tried to design the operation. Safety, of course, is at the very top end of everything that we do. It has to be when you're working with high pressures, because high pressure reactions are dangerous. We're working with supercritical CO2, so we actually fill our vessel with CO2 up to about 300 times atmospheric pressure, so 300 bar, and at temperatures up to about 125 degrees C. So they're quite forcing conditions, and we wanted to be able to work safely under those conditions. And also, we're going to make polymers. So polymers are plastics. They can be like glues. They can be thick. They can cause all kinds of problems in any kind of reaction. And we were going to be doing that under high pressure. So we wanted to make sure that we wouldn't be causing any safety issues through making the kind of polymeric systems that we were making. And so some of the safety features that we've built into the apparatus were designed around that principle. How can we be sure that we're not going to cause ourselves a problem? And in the video, you'll see one of my co-workers and me explaining how we have a safety valve that ensures that all the pressure is released carefully from the reaction before we open up the vessel. So those are really important aspects that we had to think through as we were designing the apparatus and as we were trying to set things up. We also introduced a method of doing some stirring, agitation, and initially we were using magnetic fleas, as happens in many chemistry labs, but they weren't sometimes powerful enough to stir the conditions that we were working with, because we were creating some thick and viscous polymeric systems. So we've since moved on to a direct magnetically coupled stirrer that has quite a lot of torque associated with it. And I think Andrew will mention that when we come to thinking about the pressure syn vessel and how that's evolved as well. So the vessels that we use in our group, we have about 35 of them in our laboratory, and they're used by all of the researchers in our labs. We have research visitors who come in and use them. We have undergraduate students doing projects who use the vessels, and all of these are done after each individual has been trained and we actually have a high pressure course that all of our individuals undergo to make sure they understand all of the issues around high pressure. That's something else you might want to consider about how you handle the logistics around safety training. But these high pressure processes are really quite common around the world. So supercritical CO2, as I said, it's around about 300 bar and up to, in our case, up to 125 degrees C. And we're working in our lab in scales of around about 60 to 100 milliliters. We have designed a vessel that's 1 liter that we use for our scale up. And that's quite a big step up, but that helps us to take things towards commercial processes. But I've been involved in visiting people around the world, and I've seen some really large high pressure kits. So, for example, in southern France, northern Spain, and Portugal, there are very large supercritical fluid apparatus that are there to clean up cork wood. So the wood that's used to form a cork in a bottle of wine, and they use supercritical CO2 to do that. And there are vessels that are around about 25,000 litres in size. So the scale can be really quite high. And similarly, there are plants around the world that do decaffeination of coffee and cleaning up foodstuffs. So supercritical fluid vessels are everywhere and very popular and commercially viable. But my interest was in creating small scale equipment that we could work with. So Andrew went through a lot of the safety implications that you need to mention, and we've done that, and you'll see some of that mentioned in the video you're going to see. The only other thing I would add is that if you're working with CO2, you need to make sure you're in a very well ventilated room, because if you release all the pressure that's inside the autoclave into a room that's closed, you might build up sufficient CO2 that you asphyxiate any living people inside that lab. And that's something you really want to avoid. So you should always check very carefully the size of the room, the ventilation of the room, and how much CO2 you're going to be potentially putting in there if your vessel vented very quickly. That's a really big safety aspect that we take very seriously. Okay, so what I've done is I've just given you a little bit of an outlook of the kind of things we tried to do and why we did that. I think probably now it's over to you, Andrew, to go through the video and see what we can see.
Yeah, well, thank you. Thanks for that, Steve. As I said, Steve has been using these vessels, as Stephen said, for a number of years. And in that true fashion, this is a case study that we prepared earlier. So this runs for about 12 minutes or so. I'll just set this running.
So welcome everybody to the Polymer Chemistry Lab at the University of Nottingham, School of Chemistry. I'm Steve Howdle and I'm head of school. And my scientific interest has always been in using supercritical fluids to make polymers. And so we've been doing that since the 90s. And I guess what we've done is developed a lot of expertise to help us to pull together the apparatus to allow us to make polymers. And we're interested in that because we do it in a clean way, and we can make some polymers that will be difficult, or perhaps even impossible to make in the same way in a normal solvent. So let's cut to the chase then. What do we do? Well, we do all our chemistry in one of these. So this is a 60 milliliter high pressure autoclave, and this is the business end of it. And you can see inside there that it's just a cylindrical vessel. And what we do is we add on to that the top unit, and we use a clamp. So here's the clamp, and I'll show you the whole thing assembled in just a moment, but we put the top bit on and we clamp it together, and that's the main sort of part of how we do things, and it allows us to work very safely. Okay, so now you can see one of our autoclaves in place. So there's the 60 ml vessel that I was just showing you. Here you can see the clamp, and what we've now done is we've clamped on the top part of the unit, around a seal, and that's given us a high pressure seal. And this mechanism allows us to very easily take it off and put it back on and clean it up reproducibly so that it doesn't leak between experiments. And the other thing that the head unit allows us to bring in is all the things we need. So we've got pipes here that can allow us to add CO2, we can inject monomers, we can put in other gases, and we've got all the safety devices to allow us to ensure that we're measuring the pressure, and then we've got a safety blow-off valve here. If something went wrong and the pressure rose higher than we wanted it to, then the whole thing would cut off. We've got electronic control here as well, so we're controlling temperature and pressure, and actually also if the pressure in our reaction gets too high, then this little box here will instantly shut off the heating and shut down the reaction. So there's an electronic cut-off as well. So from a safety perspective, that's how we build things in. All right, so now I mentioned the clamp. Here's how we just tighten it up, and I've got everything ready. And this is our unit here for tightening it up. Notice that we've got here a fairly unique shape, and this key only fits in this clamp. And this is important because the only way that I can open this up is by having this key in my hand. But this key is also the high pressure valve here, or high pressure safety valve. So this gives us the final seal. So the last thing we do is we put that in place and seal it up. And in our lab we've got something like 30 different autoclaves, but this key will only open up this clamp, so that we know that in every experiment we absolutely have control over which clamps are being used, which keys are present, and we can't ever open up the vessel with any pressure inside it, because if I want to open up this vessel, you can see I've got to take off this key, and the pressure inside will be relieved if there is any pressure inside. It's going to come out because there's going to be a hole there. So only at that point, when we know there's absolutely no pressure left behind, will I then be able to use this key to undo the clamp. That's a really important aspect of how we work safely in this department. Okay, so what we're going to do today is we're going to show you one of our reactions, and one of my colleagues, a PhD researcher, Cartini Alias, is going to take us through the synthesis of some polymethyl methacrylate using dispersion polymerization in supercritical CO2, and she's going to take you through all the steps, and so I'm going to hand over to Cartini now.
So now we are going to start the reaction. So first of all, you have to condition the autoclave under positive pressure. So now it's ready. And while I've already prepared the reactant that we need. So it consists of three things: the monomer, the MMA, and the surfactant, PDMS, and the initiator, the AIBN. So we need to degas the mixture. So I put it in the fume cupboard and then degas with argon gas for about 20 to 30 minutes, and then leave it in the ice bucket, and it's ready now. So I'm using the syringe with a long needle here. So I'll get it from the fume cupboard and bring it here. So you have to, it's like a safety measures, you have to make sure the lid is always on. So yeah, it's ready now. So we will inject the reactant through the holes. We have to remember that the autoclave is under pressure, so please doing it properly and slowly, and then take the key, okay, and then seal it back.
Okay then, so as Cartini said, she filled the reactor, and we got the monomer and the initiator and the surfactant in there, and pressurized with CO2. We went up to 3000 psi, so roughly 200 bar, and then raised the pressure, and so we got raise the temperature, sorry, so we're about 65 degrees, so we can kick off the reaction. And we just very carefully control the pressure and make sure that at 65 degrees C we have the right amount of CO2 in there to round about 3000 psi. And we know that gives us the right density of CO2 to allow our polymerization reaction to happen. And then that's left for 4 hours. And what we've got now is one that we prepared earlier, just like they do on TV with the baking shows. This one has been running for 4 hours, and we've just turned off the heating. It's coming back down from 65 degrees C. The pressure is coming down, and we're going to just monitor this as we come back down. And when it gets to round about room temperature, which we're not too far off, we're then going to open up this vessel and look inside and see what we've created. So at that point, I'll now hand back over to Kartini.
So I pretend that the reaction has completed. So this is how I'm going to show you how we stop the reaction and detach everything and collect the final product. So first of all, you have to cool down the system to the room temperature. So we set the temperature to 0, so it's about like 23 degrees Celsius now. So after it reached the room temperature, we can depressurize the system now. We have to stop the stirrer, okay, and then detach it. And then now we start to vent it. So we vent the system using the outlet tab here, and then make it slowly. We've done the depressurizing, okay. So now I've already detached all the joint, yeah, the inlet and the outlet joint, yeah. And now I'm going to open the autoclave and collect the product. So first of all, we open the key and slowly, just to make sure that they are free, they are not under any pressure, and then we open the autoclave there. So this is the detached autoclave here. So we are going to see how the product turn out. So we open the head, the autoclave head, and then this is how the product looks like. Yeah, this is the PMMA, the polymethyl methacrylate polymer. So since we are doing free radical polymerization, it's like it should be turned out as a very fine powder like this. So we know that our reaction is work well. So this is what we expected, to have a very fine, white, fine powder. So this is like the high volume scale, just to show you and give you an idea. And this is how our products normally looks like. And just to let you know, it always be a free flowing powder, because we are doing dispersion polymerization. So it should turn out as a free flowing powder.
So I'd like to just say a little bit about the difference between out of the box pressure syn and the difference between Steve's laboratory here and what they're using. So PressureSyn has some of the same safety features. The critical key that's been explained already, how that prevents you from opening this when it's under pressure, even with polymer chemistry. We have two levels of safety, pressure over safety. So we have a burst disc and a spring valve. So the spring valve will operate on a burst disc for extra protection above that. Then we have our own built-in pressure gauge, so you can see the pressure, monitor it. So you don't need any electronics beyond what you have here. For heating and stirring, as standard, we recommend the use of a hot plate stirrer. So we have this simple adapter that fits on top of the hot plate stirrer. And PressureSyn simply drops in. The adapter ensures even heat distribution into the block itself. You can mount the hot plate stirrer's temperature probe into the block, and then to measure solution temperature we have a standard K-type probe. So you can then measure with a thermocouple the temperature of your solution. So very simple, with all the safety features you've seen today, but in something that can work off the shelf in your laboratory on a standard hot plate stirrer. Now if you want some of the additional features like the magnetic drives, etc., these are things we're happy to discuss, and many of our customers do want something bespoke, made to measure, to do exactly what they want. So we can do that without any issue.
I hope that that was informative. Definitely gave gave a nice insight into how Steve and the group had been using the reactors. So I left the video running a little bit later within that section, just to introduce some of the features that we can add and that are built in with the reactor. So after playing that video, Steve, is there any comments that you would like to add to with your experience of using PressureSyn in the extensive research that you carry out at Nottingham?
Not really, no. I think my comments earlier and the video really explained everything that we tried to achieve, and it's taken us about 15 to 20 years we've been developing this. So we've tried and tested a lot of the things that you've seen, and generally things work really well in the lab. We designed it for high pressure operations. And of course, we mainly use it for processing polymers and synthesizing polymers, but there's no reason why the same apparatus can't be used for other types of chemical reaction processing, as you mentioned yourself, Andrew. So I'd be very happy to take some questions if there are any individuals who have any particular questions.
Yeah, for want of time, I'll just wrap up quickly, and then we can take some questions, because I know we had a few technical hitches there. I think one thing that Martini and Steve touched on in the video was the unique key aspect of the PressureSyn reactor. So this means that you need the key related to the clamp and the reactor that are joined together to be able to depressurize. So that's a really important safety feature. And these are just a few things that users are really that get and gain more confidence for using these types of reactors. So as Martin pointed out, the construction is highly chemically resistant. We can add sleeves for higher and greater chemical compatibility with your chemistry, glass or PTFE. Martin outlines the all of the connections that we can add. At the end of that video, and as Stephen said, that was recorded at during lockdown a few years ago, we've actually expanded on the availability, as Steve said, of a magnetically coupled overhead stirrer drive, and that's really important for running more viscous solutions and chemistry such as the polymerization. But just to add, and continue that train, that we can supply pressurized reactors in bespoke formats. We do have a range of different volumes and reactors for running parallel chemistry as well under pressure, say multi-position formats. But enough of that. So just wanted to summarize to say thank you to Stephen, Professor Steve Howdle, and the University of Nottingham working with us to develop, well, using their expertise and extensive knowledge to develop this range of reactors, the pressure Syn. This is available to all of you. We've taken the university's experience to really design a product that is really fit for purpose. So, for want of time, and I want to see if I can get some questions from you guys about what you've heard today. I'll leave the floor open. Hopefully, some of you have dropped down some questions in the chat box. But if not, please unmute yourself, and if that option's available, and we're open to any questions.
Thank you, Andrew. Thank you, Steve. Just to remind everyone that you can post questions both in the chat and in the Q&A, and we'll address them wherever they are. If no one has any immediate questions, any jacketed reactors?
So we are able to both heat and cool with different solutions. A heated or cooled jacket is available for these reactors. Yeah, so yes, we can.
Down to specific sort of external requirements or compatibilities, but there's many different ways that we can heat or cool reactors. I think internal coils, electrical jackets and whatnot are also options. Yeah. I thought I would supply a question of my own. Oh no, we've got more. Can these reactors be equipped with baffles for liquid reactions?
Well, we can supply both glass and PTFE sleeves. So I guess a design, it's not a question that I've been asked, but a modification of one of those could include not baffles, but maybe some internal geometry to create more turbulent mixing.
Of sodium hydroxide or potassium hydroxide. I think when we're talking about chemical compatibility, this is where we start getting into the particulars about the ratings for different temperatures and pressures, because essentially that will take into consideration these calculations of the sort of risks of different grades of materials.
So obviously stainless steel and glass wouldn't be appropriate with high concentrations of hydroxides, but PTFE is perfectly compatible, and we can line the reactors with that.
Yeah, I know that it really does depend on what temperatures and what other conditions are involved when it comes to these, very highly acidic or alkaline reagents. In the case of an emergency, when running a reaction in an autoclave at high pressure and temperature, is it safer to cool the reactor first or to release the pressure immediately?
That's an interesting question, if I could take that. So our practice is a bit of both. So we have it set up so that if the pressure overcomes a certain level, we turn off the heater. And the heater then turned off, and then the thing will start to cool down and pressure should go down. We tend to pitch that a few bars below where the safety relief valve will kick in. But if that failed and the pressure continued to rise, then a safety relief valve would automatically blow and all the contents of your vessel will be released up into the fume cupboard, because that's where we do our reactions. So we always try to release things by lowering the temperature first, turning off the temperature. But if things did go badly wrong and the temperature couldn't be turned off, or it didn't respond quickly enough, then we have pressure relief valves that can release through a burst disc or through a spring-loaded mechanism.
Thank you, Steve. That was really insightful, I think. I have another question. Do you have any gas-inducing stirrers for gas-liquid reactions, which recycles the gas from the gas cap, e.g., a hollow axle stirrer?
I guess it's an interesting question for recycling gas.
We have done that before. Sorry. We've had some high pressure systems we supplied to the USA, which had exactly that. I can't remember what pressures we were working at. I think about 20 bar. It certainly had a gas feed through the stirrer and then the impeller.
Thank you, Martin.
Nothing on there.
I'm not seeing any more questions in the chat immediately. Or in Q&A.
I've got one question, Steve. How do you introduce high pressure CO2 into the reactor? How do you pressurize your reactors?
Okay, so we use specialized pumps that take liquid CO2 from a cylinder. These pumps keep the liquid cold, and then they sort of hydraulically pump it into the vessel, and we pump it in cold, and then we heat it up to the temperature we require. Another route is to have a thing called a syringe pump, which is a little bit like a bicycle pump. You know, you have a cylinder full of gas that is then squeezed by pushing the gas through. So those are the two things that are used quite regularly in research around CO2. So they're very easy to set up and very reliable.
Thank you. So just another opportunity to ask any questions for the team here and Steve. I would say if not, you're always welcome to drop any questions. I know it can be difficult to think of these on the fly. You can drop any questions to us and we'll answer them after this webinar. Say that this webinar has been recorded, so if you want to review anything that you've seen or are interested in Steve's work or the Pressure-Syn and Asynt range of pressurized reactors, then feel free to contact us as well. So with that, and I know we had a few technical hitches, but thank you very much for joining. I hope this has been informative. I hope you've learned something. Thanks again to Professor Steve Howdle for his insights and his assistance and expertise in developing these reactors. And thanks for your time and questions. So look out for the next webinar. If you have a topic of interest that you'd like us to cover, then please let us know as well. But anyway, thank you for your time, and we'll see you next time. Thank you.
Thanks, everybody. Bye-bye.